of just kind of vocabulary, really mostly, with triangles and the angles in triangles. Our goal for today, really, the only things I want you to be able to do is I want to remind you about how to classify triangles by sides and angles, which I'm sure you all know how to do. We want to be able to find missing angle measures in triangles, solve algebra equations based on triangles, just stuff like that. We all know what a triangle is, right? Three segments that meet at three different vertices. Vertices have to be non-collinear points, or it would be a line, it would be an angle, triangle. We know that when we classify triangles by sides, there's only three possible ways we can categorize them. Either they're equilateral. Obviously, what's that word mean if we break that word down? Equilateral. Equa means same sides. There you go, same sides. So equilateral has a triangle. Any triangle with three congruent sides is equilateral. Okay, isosceles. This is a little tricky. I mean, it's not tricky in a hard way, just tricky in a definition way. What's the definition of an isosceles triangle without looking? It's got two congruent sides. Okay, not quite. It's a little. Were you gonna say something different? Okay, I cut you off. Felt bad. An equilateral, or excuse me, an isosceles triangle is a triangle that has at least two congruent sides. So it's kind of a weird case, but an equilateral triangle is yes or no, also isosceles.
Yes.
Yeah, it is. It is. It could have three congruent sides. To me, that's almost. I'm not really sure why we say that. I guess, but I don't know. I mean, there must be a reason. That's a pretty weird case though for an isosceles triangle. Honestly, when we categorize triangles, unless you're trying to be tricky on a test or something, we would rarely, if ever, call an equilateral triangle isosceles because we always want to be more specific if we can. What's a more specific way of describing a triangle that has three congruent sides? Isosceles or equilateral? Equilateral. So we'd always call it equilateral, right? Yes, sir.
Isn't it kind of like how a square is technically right?
It's similar to that, right? We could say that a square is a subset of the set of rectangles, but we'd prefer to call it a square, wouldn't we? Because that's more specific. And then the other possibility would be, what if none of the sides are congruent? That's what we call scaling, right? What about angles? If we categorize by angles, an acute triangle obviously has what? What's the definition of an acute triangle? Well, in fact, it has to have. Go ahead, Jesse. Say it again. Okay, and one angle or two angles or three angles, how many? That'd be three, wouldn't it? That'd be all three, right? Where all three angles are acute, which means that it's less than 90 degrees. Good. Definition of acute angle is less than 90 degrees. What about an equiangular triangle? Well, if you take that word, it's pretty obvious. Equa, same, angular, angle, right? So same angles. Any triangle that has three congruent angles is equiangular. What would the measure of each of those angles have to be? 60. Good. 180. We all know that. We haven't gotten to this yet, but I'm sure you remember this. The sum of the measures of the interior angles in a triangle is always 180. There you go. So 180 divided by 3 is 60. What's always the relationship between equiangular and equilateral? Same, aren't they? Right, we'll get to that. Equiangular triangles are always equilateral and vice versa, right? Obviously it has to be acute too, doesn't it? Because the angles are all 60. Okay. Right triangle has how many right angles? One. You can only have one, can't it? Because a right angle has a measure of 90 and you only get 180 degrees to spread around. So there's only angular room, if you want to think of it that way, for one right angle. Okay, I got one for you. What's a nice convenient way of describing the measures of the two acute angles in a right triangle? What's something that has to be true? They equal 90. What's another way of saying that? Complementary. Yeah, good. So the acute angles in any right triangle are always complementary, aren't they? Right. Okay, what about an obtuse angle? Obviously, there's only room for how many obtuse angles? One. So an obtuse triangle would be one, a triangle with one obtuse angle. What if I did this? What if I just tweaked this ever so slightly and I told you this additional information? What does that tell you about that? How could I be more specific? How go ahead, Kate. That's right. I'm saying that means, those markings mean they're congruent. So how could I be more specific than saying just obtuse? It's obtuse what? If it's got two congruent sides. What I hear? Oh, there you go. Isosceles, yeah, okay. And so whenever if we have enough information, we'd always like to pin the triangle down as precisely as we can. We'd like to be able to categorize it by both its sides and its angles. We always want to, when we do that, there's an order. We always do the angles first, and angle A comes before S, right? Angle and side, so you do the angles first. So we'd say this is an obtuse isosceles triangle. Now let's assume that this is a right angle, and that as it's drawn here, all of the sides have different lengths. How would I most precisely describe that triangle? It'd be a right scalene triangle, wouldn't it? Okay, right because it's got a 90-degree angle, scalene because the sides are all different. Okay? Parts of a triangle, I mean, this is just total review. Remember that we all know what adjacent sides are, right? Adjacent means next to. So if we're referring to the angle at vertex A, then we know these are the adjacent sides, that's the opposite side, no big deal. I mean, you guys all know that. We know this too. For a right triangle, we get some specific terminology that applies. For a right triangle, we'd say that if this is the, I probably don't even need to say this, but if this is the right angle, we always know that the hypotenuse is the side opposite the right angle, right? And the two sides that are adjacent to the right angle are the legs, right? So that's specifically how we'd refer to the sides in a right triangle. And then also for an isosceles triangle, we're specific there too. As long as the isosceles triangle only has two congruent sides, we would call those two congruent sides the legs, and the oddball side would be the base. Okay? And what else? We can skip this. That's no big deal. Okay, this is the other thing I wanted to just remind you about. Exterior angles. Okay, so I didn't make this slide, it's a little goofy, but it does the job. So the smiley faces all represent all of the interior angles, right? We know that the sum of the interior measures of the interior angles is 180. You already told me that. The hearts represent what we call exterior angles. Do you remember talking about this back in middle school? Or is this something new? Maybe it's a little new? Okay, so here's how we create an exterior angle. If you take any side in a triangle and you just extend it through a vertex off to infinity, you're going to create an obtuse angle, right? Let's just take this one for example. Everybody see that if I take side AC and I extend that through vertex A out to infinity with a ray, I'm creating a straight angle, which we're not worried about, but I create an obtuse angle next to the triangle, right? Now, it wouldn't have to be obtuse. There are some situations where it might even be acute, okay? But I'm going to create some angle that's adjacent to one side of the triangle. Does that make sense? I can do that for each of the three vertices. But do you see something a little fishy about this? Does it seem like 3 is enough? Are there more than 3 exterior angles? Yeah, I've seen a lot of people nodding their heads. Because if I want to create an exterior angle at vertex A, I could also use this side to do it, couldn't I? Right? I could take side AB and extend it off in that direction and create an exterior angle there, right? So, right? Now, what can you tell me about those two exterior angles? How do you know they're congruent? Oh, they're vertical angles, so they must be congruent, right? Okay, so then do you see why maybe it wasn't such a big deal that we only drew 3? Because no matter what I do, if I draw all 6 of the possible exterior angles, they're always going to come in pairs, incongruent pairs, aren't they? Right? And so for that reason, we typically only show one exterior angle at each vertex. right? Because if we showed the other one, we already know it's gonna have the same magnitude, same measure, right? That make sense? Okay, so take your pick, whichever one's more convenient to draw, that's the one we'll draw. There's a relationship with exterior angles. We know that, which of those three angles is the exterior angle? One is, okay. We know that the measure of an exterior angle to a triangle is always equal to the sum of the measures of the two remote interior angles. Now, what does the word remote mean? Away or far away, right? So another way of saying that is non-adjacent. So we're going to not worry about the angle that's adjacent to angle 1, but the other two that are non-adjacent or remote, the sums of those measures will always be the same as the measure of angle 1. Okay? That's kind of makes sense in a way, doesn't it? Because let's take our mystery angle here. Let's label it with an x. If I want to solve for x, what's one way I could do that without even using the exterior angle? Okay, would everybody agree that x plus the sum of these measures, 2 and 3, has to equal 180? Okay, how could I do it without using the triangle at all? Okay.
The linear pair.
Yeah, okay, we have a linear pair that's supplementary, and so x plus the measure of angle 1 must equal 180. Well, if x plus 1 equals 180, and x plus 2 plus 3 equals 180, then doesn't that necessarily mean that the sum of 2 and 3, those measures, has to be the measure of angle 1? They do the same thing, right? They add to 180 when combined with x. Okay? So then the next step's a pretty easy one. If we wanted to do something like this, does this make sense? If I want to solve for x here, this time the triangle by itself is not enough, is it? Right? Because I don't know what the measure of that angle is. But in this case, I could take advantage of the exterior angle theorem and say, okay, I know that this exterior angle, the measure of that exterior angle equals the sums of the measures of the two remote interior angles, which gives me an algebra equation, which is easy to solve. Solve for x, I could plug it back in and get the magnitudes of all those angles if I want to, right? Make sense? No biggie. Okay, same kind of thing here. How can I set up a really simple equation to solve for x? What geometric property am I going to take advantage of here? What's it going to be? It's a right triangle. Okay, so then that tells me that what's that tell me? What's important about that? That's 90. And so in a right triangle, what's the sum of the measures of the two acute angles? 90. Yeah, so 2x plus x equals 90. Whoops. So therefore 3x equals 90, x equals 30. And then we can plug those back in and get 90, 30, 60, right? Okay, no big deal. All right, that was quick. Okay,